Welcome to Chapter 5, Part 2. We're going to talk about the costs of production in this video.
To begin with, we want to talk about accounting cost versus economic costs. You are well versed on the concept of accounting costs from taking accounting, but economics costs may be another thing. When we think about accounting costs, you should think of a historical record. So accountants record the expenses that the firm actually expended. Actual money laid out. So things like wages, utilities, and rent. They also account for things like depreciation of capital, and that would be considered an accounting cost. Economists are interested in those costs, but they also are interested in looking forward and thinking about decision making. So when we talk about economic costs, we're thinking about the trade-offs that exist by making a decision. That should not be a surprise for you given your experience already in economics. When we talk about economic costs, we want to think about the total cost of using resources in production. So you can think about that as accounting costs plus opportunity costs, or explicit plus implicit costs. And so we'll talk about the difference between explicit and implicit. Explicit costs are costs for which we actually lay out money. We write a check for this, or we pay cash for this, or it's directly withdrawn from our account. This includes things like flour, sugar, chocolate chips, labor, electricity, if we're thinking about our Hungry Helen's cookie factory again. Implicit costs are the costs of production for which you don't actually lay out any money, but they involve instead opportunity costs. So opportunity cost is a term you ought to be familiar with. When we think about the opportunity cost, we often think what you give up to get something else. I like to talk about it as the value of the next best alternative. That makes it easier to incorporate it into our costs when we think about it as that value. The value of the thing we didn't get to do because we did this other thing instead. So I want you to think about Hungry Helen. Pretend Hungry Helen is trained in information technology, and she could earn a nice salary as an IT professional. Pretend that salary is $100,000 a year. If she decides to start a cookie factory, she's giving up that $100,000 a year salary. That would be important to consider when we're thinking about the implicit costs of Hungry Helen's cookie factory. Let's continue with Hungry Helen and try to sort out this concept of explicit and implicit costs, along with accounting and economic costs. So let's pretend to start the business, Hungry Helen needs $300,000. This would be to do things like buy equipment and rent a building or buy a building, those kinds of things. And let's also assume that the interest rate is 5%. Let's assume that that interest rate applies to both savings and if you borrow money. This just simplifies our analysis. So let's say that Helen takes the $300,000 from her savings account, and she takes that $300,000 and puts that into capital equipment. In this scenario, there really aren't any accounting costs. The accountant is going to look at that $300,000 in cash and say that $300,000 was an asset as cash, and now that $300,000 is a physical asset on the books. However, the economist will say, well, you could have earned interest on that $300,000. So if the interest rate was 5%, you could have earned 5% on that $300,000 or $15,000. There is an opportunity cost then of taking that savings and using that savings to start the business. So we would say here there's an implicit cost of $15,000 in foregone interest. Let's look at scenario 2. Let's say that she takes the $100,000 from savings, but also gets a loan for the other $200,000. The accountant, again, will not really be looking at the $100,000 from savings, but they will say that there's a cost associated with the $200,000 loan. For simplicity's sake, let's say you borrow the $200,000 at the beginning of the year and you pay the loan back at the end of the year using simple interest. The interest on that loan would be $10,000. That's an explicit cost. We actually have to write out a check for that additional $10,000 on top of the $200,000 that we're paying back. For the economist, the cost has not changed. It's still $15,000. There's the $10,000 in loan interest, as noted by the accounting costs, but there's still an implicit cost. Hungry Helen is taking $100,000 from her savings, and she is foregoing 5% interest on that money. So $100,000 times 5% would give us $5,000, $10,000 in actual money paid out, plus $5,000 in money that is just foregone. The economic cost is the same. It's still $15,000. So you notice there's a difference in the way the economist thinks about this and the way the accountant thinks about it. That's not to say accountants aren't forward-looking and aren't using that historical data to make decisions. They certainly are. Another cost I want you to think about is this concept of sunk cost. So we often make poor decisions because we can't leave sunk costs alone. If you're really interested in digging into this concept of sunk cost more, I encourage you to Google sunk cost fallacy. If you Google this, you're going to find all kinds of interesting and funny examples regarding sunk costs. Sunk costs are money that have been spent already that cannot be recuperated. Our job as educated decision makers is to ignore sunk costs when we're making decisions. So I'm going to use an example here. Pretend you bought a car and that car cost you $1,500. The current market value of the car is $2,000. Now you're having some issues with the car that do make it seem like you probably are going to need a kind of expensive repair where you need to get the transmission fixed, and that repair would cost $800. Should you make the repair or not? Now the typical student would say to me, you don't make the repair. If you add $1,500 plus $800, you get $2,300, and that's too much money to spend on a car that's worth only $2,000. However, the $1,500 that you paid for the car is a sunk cost. So ignore the sunk cost and say, the market value of the car is $2,000. The cost of the repair is $800. Since the value of the car is greater than the cost of the repair, we should make the repair. I know that goes against what many of you think, but that's really what we should do. Continuing with our definitions of cost, we should define something that we call total cost, and I like to insert in here the word economic, because I want you to think about total cost from that economic perspective, where you're thinking about all costs that a firm faces in making the decision to actually produce the good. This is really important when we get into talking about economic profit. If we have a good understanding of economic costs, that will make it easier to understand economic profit and the difference between economic and accounting profit when we get into that. So when we talk about total costs in economics, we mean all the explicit costs, the things that you actually pay money for, and all the implicit costs, those values of the next best alternative that we give up when we do a particular production or supply a particular service. Total cost is fixed cost plus variable cost. So we should define carefully fixed costs and variable costs. The fixed costs are costs that do not vary with the quantity of output. So these are costs that I have to pay whether I produce 0 units of output, 10 units of output, or 1,000 units of output. These costs would be the same regardless of the number of units of output that we decide to produce. Once we enter into a lease on a building or a lease on machinery, those are fixed costs. If we decide not to produce cookies anymore, we still have to finish paying out the lease on the building and the lease on the machinery. It's the same with salaries. If we have salaried employees that we've agreed to pay a fixed amount per week or per month, those things are considered fixed costs. So we pay that fixed salary regardless of the quantity produced by the firm. Things like insurance could also be fixed costs if we're talking about insuring the building, the machinery. Those kinds of things would be fixed costs. If we're talking about something like workers' comp insurance, that's actually a variable cost. So I could have been more explicit here, but a lot of our insurance is actually considered a fixed cost. Then we have variable costs. Variable costs are costs that vary with the quantity of output that we produce. So if we produce only a few units of the good, then we have relatively low variable costs. If we produce lots of units of the good, then we're going to have higher variable costs. So examples of variable costs for our Hungry Helen's Cookie Factory include things like utilities, flour, chocolate chips, and wage labor. If we're not producing very many cookies, we don't need a lot of flour, chocolate chips, or workers. We also don't have to pay a lot of electricity and gas and water for the firm. We also need to think about marginal cost. Marginal cost is actually super important when we're making the decision for the firm on how many units to produce. You hear the word marginal, so you should be thinking delta over delta, change over change. Marginal cost is the change in total cost when output increases by 1 unit. So if we decide to produce 1 more dozen cookies, how much will cost go up by? That's the change in total cost over the change in quantity. You guys know from thinking about principles of economics, when we talk about marginal benefit and marginal cost, the firm only decides to do the thing, or the consumer only decides to do the thing, as long as the marginal benefit is greater than or equal to the marginal cost. So you should be thinking that this marginal cost is going to be really important to us down the line as we begin to talk about profitability for the firm. Other costs that we need to think about. These are going to determine things like whether the firm shuts down permanently or shuts down temporarily, and also going to help us eyeball the profit that the firm actually produces. So the average total cost is the cost of producing a typical unit of output. For average total cost, what we do is take the total cost to the firm and we divide it by the number of units that the firm produces. So total cost per unit, that's actually what average total cost is. Average fixed cost is the fixed cost attributable to the average unit of output. So we have a big stack of fixed costs. If we're producing very few units of the good, then each unit of the good bears a high proportion of those fixed costs. As we produce more and more units of the good, those fixed costs are able to be spread over more units of the good, and so the average fixed cost will go down. For average fixed costs, we take the fixed costs and we divide by the number of units. Notice, for our marginal cost, we had delta over delta. For our averages, we just have total over quantity. Average variable cost is the variable cost per unit produced. So if we're looking at producing our cookies, let's say we talk about a unit being a dozen cookies because we sell our cookies in dozens, then we're going to be thinking about how much labor, electricity, flour, chocolate chips, all of those things cost per dozen cookies that we produce. To figure that out, we take the variable cost for the firm and we divide that by the number of units that the firm is actually able to produce. These things are going to help us decide, again, like I said, whether the firm shuts down permanently or temporarily and how much profit there is for the firm. It should be noted that because total cost equals fixed cost plus variable cost, we also know that average total cost equals average fixed cost plus average variable costs. Let's do a few calculations here. So for total cost, let's take our fixed cost plus variable cost, and that gives us total cost. So 50 plus 0, if we produce no units of the good, we still have to pay $50 in fixed cost. We've got to pay for the building, the machinery, and those kinds of things. But we're not laying out any money on flour, chocolate chips, labor, and so on. If we produce 1 unit, we have 50 plus 50, or $100 in total cost. If we produce 2 units, we have 50 plus 78, or $128 in total cost. Now, marginal cost, what you're going to look at is the change in cost. And we typically do the change in cost over the change in quantity. So 100 minus 50 over 1 minus 0. Now, because I've increased our output by increments of 1, our denominator here will always be 1, so there's no need actually to put a denominator in here, but it's possible that we could have that denominator in tens or 20s or hundreds. So we want to make sure that we remember that we need to do that divide by if we're looking at something other than going up by 1 unit. Our marginal cost here, or how much cost is added when we produce that first unit of output, is 50 units. When we produce that second unit, we're adding $28 to our total costs. You may notice that the change in variable cost is the same as the change in total cost. And that's because fixed costs are just that, they're fixed. So to calculate marginal cost, you could look at the change in total cost over the change in quantity, or you could look at the change in variable cost over the change in quantity. Those two things will actually be the same. Average fixed cost, we would take our fixed cost of 50, divide by the number of units produced. If we're only producing 1 unit, all $50 could apply to that 1 unit, so it's $50 per unit. If we're producing 2 units, then each unit gets $25 applied to it. You notice as we produce more and more units that the average fixed cost goes down and down and down and down. That's the only way that that can go because that's fixed. That's not the same for marginal cost. You notice marginal cost goes down and then begins to go back up. And we'll talk about why that happens as we get on to the next page. For average variable cost, we're going to take the variable costs and divide by the number of units produced. So when we produce that first unit, we have $50 in variable cost, divide by 1 unit, it's $50. When we produce the second unit, our variable costs are $78, so each unit has $39 worth of variable costs assigned to it. Again, you notice the variable costs go down and then begin to go back up. And you'll see the same thing with average total cost. So for average total cost, take total cost and divide by the number of units produced. So if we produce only 1 dozen cookies, the variable costs and all of those fixed costs get applied to that 1 dozen cookies, and that 1 dozen cookies has a cost of $100. If we produce 2 units, it's $128 in total cost. Each unit has $64 in cost attributed to it, and you notice that goes down and then begins to go back up again. We're going to understand a bit more about why that happens once we look at these cost curves. If you look at the total cost and the variable cost curves here, you'll notice an interesting shape associated with those. The fixed cost is not so interesting, right? It's this really flat line here. It's actually perfectly flat because we have output on this axis and cost on this axis. Fixed costs do not vary with output. So if we produce 0, we have $50 in fixed cost. If we produce 5, we also still have that same $50 in fixed costs. And if we produce 13 or 100, whatever it is, we still have that same $50 in fixed costs. What you notice about the variable costs is that they initially go up slowly. And then there's a point at which they turn, and then they begin to go up more quickly. And because that happens to variable cost, that same behavior happens to the total cost. Because total cost is just whatever fixed is plus whatever variable is, and that gets us up here to total cost. The variable cost has this shape for the same reason that our production function had the shape that we talked about in the last chapter. In the last chapter, we talked about production going up quickly initially and then flattening off as we added workers. Remember, those first few workers added lots of productivity, but then as we added more and more workers, they didn't add as much output as the previous workers. That shape and what's going on behind that is actually what's happening here. When we're producing those first few units of output, we're actually getting more and more efficient with those inputs that we're adding. because we're taking advantage of those economies of scale that are happening with the division of labor and those kinds of things that we talked about with labor. But there is a point at which we can't continue to gain from adding those additional workers in the same fashion. In other words, our marginal productivity begins to flatten off. As marginal productivity begins to flatten off, we're not adding as much more output per worker as we were before, but we're still adding those costs of hiring the worker. So costs are going to go up faster. This happens because of those diminishing returns that we talked about before. And then to look at the average cost functions. So I actually took that table of data that we finished filling in, and I put that into Excel so I could produce those graphs exactly as they are in that table. It's always easy to identify the average fixed cost curve. The average fixed cost curve is always the one that starts high and then asymptotically approaches the x-axis, or the output axis here. So this guy, that's our average fixed cost. Average fixed cost is the easiest one to identify, and it's also the least useful one for us when we're doing any kind of decision making. The average total cost always starts relatively high. So the average total cost is going to be the curve that lies above all of the other curves for most of the time that we're looking at this. That's because we're taking these fixed costs and the variable costs to get that total cost curve. And so the green curve, it appears to be the green curve is the one that we're adding to the pink one to get that total cost. If you saw that ahead of time, you were right. That's your average variable costs. The marginal cost is usually a J-shaped curve. So you see that here. It goes down, it hits a minimum point, and then goes up. When it comes up, you're going to see the same thing that we talked about with productivity. The marginal drives the average. So when the marginal is below the average, notice here the average variable cost, when marginal is below it, the average variable cost is going down and down. When the marginal cost crosses the average variable cost, the average variable cost starts to go back up. I did just notice I said variable cost on that green curve, but I labeled it fixed cost. The green curve should be average variable cost. My apologies for the mistake. You also notice as average total cost is above marginal cost, average total cost is falling, falling, falling. When marginal cost crosses the tippy bottom of average total cost will turn and start to pull back up. When the marginal cost of producing that next unit is higher than the average begins to get pulled up. The marginal cost is higher than the average here. The average is getting pulled up.
Now that we've completed our discussion of short-run costs, let's look at the long-run costs.
So we have to first define long-run costs. When we're talking about workers, the cost of a worker is really their compensation bundle, which we're just going to call wage. But capital is more complicated than that. So we need to define the user cost of capital. And we're going to use the little symbol R here for the price of capital. The user cost of capital is really the opportunity cost of holding your funds in physical capital. This includes the interest foregone on savings or the interest paid on loans. But we also have to include the value of the machine that is diminished through use. In other words, the user cost of capital includes both the opportunity cost of holding the funds as capital and depreciation. So to think about this, we'll let little r equal the user cost of capital, or we often call it rent. That doesn't necessarily imply that you're renting the machine, but just that we want to talk about this as rent. C is the value of the capital. Let I be the interest rate and D be the depreciation rate. So we define the user cost of capital as the interest rate times capital plus the depreciation rate times capital. This piece is the dollar value of the interest that's foregone or that's paid as a loan. And this piece is the depreciation of that capital. So for example, if we had capital equal to $100,000, an interest rate of 5%, and a depreciation rate of 10%, our user cost of capital would be 0.05 times 100,000 plus zero point 0.1 times 100,000, or 5,000 plus 10,000, where the user cost of capital would be $15,000 per time period. We've talked about the firm's ISO quants, the combinations of capital and labor that we know will produce a given amount of output. The ISO cost line represents all the combinations of capital and labor that can be purchased with a given budget. In other words, a fixed amount of cost. An ISO cost line looks much like our budget line for the consumer. So let's suppose that we have a cost of $100,000 and that the user cost of capital is $10,000 per unit and that wages are $10 per worker hour. If we spend all of the budget on capital, we would be able to hire cost over user cost of capital. We'd be able to hire 10 units of capital. So if we spend all of our money on capital, we could hire 10 units of capital. If instead we spent all of our money on workers and no units of capital, we could hire 10,000 worker hours. Or with that same fixed cost, we could hire combinations of capital and labor that fall on this line. We should also note that the slope of this line is negative wage over rent. So for this particular line, our slope is negative 10 over 10,000, or negative 1/1000. That tells us for each unit of capital the firm gives up, they can hire 1,000 workers. Now let's look at a couple of scenarios where changes occur with regard to that ISO cost line. So suppose instead of having that wage of $10, the wage falls to $5. So we know that the quantity of capital we're able to buy does not change because our rent has not changed and the cost is still fixed at 100,000. However, we should get a rotation of the line that allows us to buy more units of labor for that same cost. So we would get an ISO cost line that would, instead of intersecting at 10,000, it would now intersect at 20,000 on our labor axis. And we would be able to buy more units of both capital and labor because of the decreased price in labor. What if instead of a decrease in wage, we have an increase in the cost that the firm is willing to spend? An increase in the cost would mean that we could hire both more capital and more labor all along the ISO cost line. So we would get an ISO cost line that would look like this. Instead of 10 or 10,000 or some point between 10 and 10,000, we would have 20 units of capital we could hire, 20,000 units of labor, or some combination between 20 and 20,000. The firm's optimal choice of inputs. This problem will look similar to what we did for consumers, but it works in a little bit of a different order. The firm is going to pick the least cost isoquant that will produce a given quantity or a given Q. So the firm is going to pick its output goal. When the firm picks the output goal, that determines which isoquant the firm is on. So the firm, let's say, is going to have an output goal of 150 units. The firm is now going to look for the least cost isoquant that they can get to produce that output. So if we look at the green ISO cost line here, we see that we can produce this quantity of output using this combination of capital and labor or this combination of capital and labor. But you'll notice that they could decrease the cost by shifting that ISO cost line inward and still be able to produce the 150 units of output. So the firm will attempt to decrease the cost to the bare minimum cost they have to spend to produce that fixed amount of output. That occurs right here, where the slope of the ISO quant line is just equal to the slope of the ISO cost line. This point will be the optimum. One more thing that we need to know about is something called the expansion path. When you think about the expansion path, you should think about the capacity of the firm. So the firm can be smaller or the firm could be bigger. The expansion path is a bigger or smaller firm based on their output goals. The expansion path is the line that represents the quantities of capital and labor a firm should use to produce the quantities of output that it may choose while minimizing the costs. So if we have this given output goal, let's say this is output equals 100, the firm would optimize by choosing the point where those two lines are just tangent to each other. What if instead we had a higher output goal? Well, again, the firm would optimize by choosing the minimum cost that would allow them to produce that amount of output. Choose the point here for capital and labor that would minimize the cost. Let's say this is a quantity of 150. But suppose instead that the firm had the output goal of 200. So if the firm has the output goal of 200, we want to be able to find the quantities of capital and labor that would minimize cost. We'll find the minimum cost then to produce that unit of output. So the firm would want to be producing right here. If we connect those dots, we actually derive the expansion path for the firm. The expansion path shows all the combinations of capital and labor the firm should hire to produce its output while minimizing costs. So the purple line here is our expansion path. Along this purple line, every point is an optimum for the firm in the long run. Now, if we were to actually work through a problem like this, we would follow this set of steps. The firm sets the output goal. That tells us which ISO quant the firm is on. We would then find the expansion path equation, the equation of that purple line that we had there. To do that, we would set the slope of the ISO quant equal to the slope of the ISO cost curve, and then we would simplify. When we finish that particular step, we will have an equation where K is a function of L. We then use that result from step 2 in conjunction with the production function. We would have at this point two equations, two unknowns. And we would use those two functions to determine K star and L star. If we're interested in the minimum cost then associated with this level of output, we would plug K and L back into the cost equation to find the minimum cost associated with the output goal.
Now we'll work through a couple of problems similar to things you might encounter.
Suppose the firm's production function is given by the expression Q equals 10 times K times L. The current wage is $5 per unit of labor, or $5 per worker hour, while the rental price for capital is $100 per unit, or per machine hour. Suppose that the firm's output is 2,000 units, or 2,000 units per hour of operation. Further, suppose that the marginal products of labor and capital are as given. The marginal product of labor is 10K and the marginal product of capital is 10L. Determine the combinations of K and L the firm should hire to produce their output goal while minimizing the cost of production. So let's use the steps that I laid out in the PowerPoint. So the output goal was given as 2,000 units of output. The second step was to find the expansion path equation. To do this, we're supposed to set the marginal product of labor over the marginal product of capital equal to the ratio of the wage over the rent, or the slope of the isoquant equal to the slope of the ISO cost curve. So the marginal product of labor is 10K. The marginal product of capital is 10L. Now, I've had a couple of people ask me, why is the marginal product of labor having a K in it and the marginal product of capital having an L in it? Why isn't it the other way around? Well, remember that how productive a worker can be depends on the availability of capital to them. So the more capital that's available, the more productive our workers can be. It's the same with capital. The more labors that are available for that next unit of capital, the more productive that unit of capital can be. Okay, back to what we were trying to do. 10K over 10L equals 5 over 100. We'll just simplify this. So this is actually K over L equals 1 over 20, or L equals 20K. So this is our expansion path. Remember, this tells us all the combinations of capital and labor that we would hire at all of the various output levels to minimize the cost of production. So no matter what level of output we're producing, the firm should hire 20 units of labor for each 1 unit of capital. Again, I've had some students ask me, why is it 20 labor per 1 unit of capital? Well, think about this equation. If I plug 1 in for K, 20 times 1 would give me 20. L would be 20. So each time K goes up by 1, L has to go up by 20. For step 3, we're supposed to combine the production function with the expansion path and find K star and L star, or the optimal amounts of capital and labor that the firm should hire. So our production function was Q equals 10 times K times L. I should have probably added in here and the output goal, because we need the output goal in here too to be able to actually have only 2 equations and 2 unknowns. Recall that the output goal was 2,000 units. So we plug in 2,000 where the Q is equals 10 times K, and then I have L is a function of K, so where the L is, I can plug in 20 times K. So the left-hand side here is still 2,000. On the right-hand side, I really have 10 times K times 20 times K. So that's 200 K squared. I'll divide both sides by 200. And this side becomes 10 because I get these 2 zeros divide out. On this side, all I'm left with is K squared. When we have squared and we're trying to get the variable by itself, we take the square root of both sides. So K equals the square root of 10, which is 3.16. So 3.16 is our K star. Now, to solve for L star, we could take that K star and our 2,000 and go back to the production function, because that was one of our 2 equations, 2 unknowns, or we could just use the expansion path. The expansion path is easier because all I have to do is plug in K and out comes L. I don't have to do any rearranging. So I would take the expansion path, L equals 20 times K, plug in the 3.16. L equals 20 times 3.16. That means L equals 63.2. And now this is our L star, the optimal amount of labor that the firm would hire to produce 2,000 units of output and to minimize the costs. And as I mentioned in class, we may want to estimate the cost to the firm of hiring these quantities of the input. You may recall that step 4 was to plug K star and L star into the cost function to find the minimum cost associated with the output goal. Well, we didn't actually define the cost function yet, so we should do that. Cost equals wage times the number of units of labor plus rent times the number of units of capital. So for us, cost is $5 per worker hour times the number of workers, which would be 63.2, plus the hourly cost of a piece of machinery, which was given to be $100, times the number of units of machinery, which was 3.16. So this equals 316 plus 316, or $632. This is the cost per hour of producing our optimal level of output. For the second problem, we'll address a short-run question. The short-run cost function of a company is given by the equation total cost equals 200 plus 55Q, where TC is total cost and Q is the quantity of total output. Both of these are measured in thousands. What is the company's fixed cost? There are two ways to think about this. I could start by letting Q equal 0 and plug that into the total cost function. Remember that fixed costs are costs we pay whether we're actually producing any units of the good or no units of the good. So total cost of 200 plus 55 times 0 would give me 200. This 200 has to also be our fixed costs. So this is 200 or 200,000. The other way to look at this is to zoom in carefully at our total cost function. Our total cost function has a constant and a piece that's actually determined by how much quantity is produced. If we think about this very literally, this part is fixed. So that's our fixed cost. This part has a variable in it. It's determined by the quantity of output. So this part has to be our variable costs. All right, if the company produced 100,000 units, what would its average variable cost be? So if we're talking about producing 100,000 units, Q is 100, because remember these are measured in thousands. What would the average variable cost be? Again, two ways to go about this. We could start by finding the variable cost. The variable cost is the portion of this that does vary with output. So 55 times 100, and we get 5,500. And then take that and divide it by the number of units that we actually produced. So 5,500 divided by 100, or 55, this would really mean then $55,000. The other way to do this is to take the variable cost and divide it by quantity first. And then from that, you could plug in your quantity and then find the variable cost of producing that many units. So average variable cost is the variable cost portion of this function, 55Q over Q. Average variable cost is actually constant at $55. So actually there's no need to plug in Q here. We know regardless of how many units we produce, the average variable cost of producing the typical unit is $55, or really $55,000. What would the marginal cost then be? So let's think about this average variable cost here, because remember, for marginal cost, we could find the change in total cost over the change in quantity, or the change in variable cost over the change in quantity, and those two things would be the same. Because our average variable cost is constant at $55, when we add one more unit, we add $55 in variable costs. That also means our marginal cost has to be 55, or $55,000. Another way to look at this is again to look at that total cost function. So if I'm looking at the total cost function, if it's a straight line, as this one is, the slope of this will be the marginal cost. The slope of the total cost line is the marginal cost line. Now, if this is not a straight line, then it's going to get a bit more complicated. It'll still be the slope of the line, but it won't be as easy to pull out of that equation unless it's a straight line. For those of you that have a calculus background, the first derivative of the total cost function with respect to quantity would be the marginal cost, the slope of that total cost line. And we also want to know what would be the average fixed cost. Now remember, by looking at our cost function, the fixed cost was 200, or $200,000. Our average fixed cost then is that 200,000, or 200, divided by Q, fixed cost over quantity. So if we have a quantity of 100, our fixed cost per unit is 2, or $2,000. That's all for now. Thank you for watching.